So welcome back, everyone. So let me start with a brief recap. So we looked at old school integrability, and first for the XXZ spin chain, and then for the 6-vertex model. So let me just repeat the few things that we will need today. So we had these 6 vertices, which I drew by these thick or thin lines. So here are 2 of them, and then let me just repeat all of them. So there's this one, where the thick line comes from the bottom and exits the top, or the one where the thick and the thin lines are reversed. And finally, the one where the thin and the thick line bounce off each other. And we said that we identify these pictures with their weights, so we can say that they're equal to A, these are equal to B, and these are equal to C. So this was the zero field assumption that these are equal, and this is, well, these are the 3 different vertex weights that you then get for the 6-vertex model. And we had, so what else did we have? Well, we had a summation convention for internal lines, meaning edges connecting to vertices, and for periodic boundary conditions. And for instance, this allowed us to say that the partition function z is actually equal to the picture where I have a number of horizontal lines with these periodic boundary conditions drawn like that, and a number of vertical lines like that. So here are K lines, here are L lines. And last time what we did is we sliced this lattice into horizontal pieces, and then we called this each piece the transfer matrix, and we saw graphically that this can then be seen as the trace, which is the trace over the Hilbert space of the kth power of this transfer matrix. And the transfer matrix is this picture here. And I think I already did this last time. I check, surely. Did I give it a label yet or not? Okay. All right, so this is the transfer matrix. And we viewed it as an operator from the Hilbert space attached to the bottom to the Hilbert space attached to the top. And what we saw by coordinate data ansatz, that firstly, if you have, well, we have commuting transfer matrices, which I will already write with this extra parameter, which is the spectral parameter. So there's a 1 parameter family of commuting transfer matrices that, moreover, commute with the Hamiltonian of the 6-vertex of the XXZ spin chain, where U is the spectral parameter. And it parameterizes all tuples ABC up to normalization, so that this combination A squared plus B squared minus C squared over 2AB is equal to delta, where delta is the delta of XXZ, and this is fixed. So we have 3 parameters, but up to overall rescaling and up to fixing 1 constraint, we have 1 degree of freedom left, which we call the spectral parameter. And then for any 2 values of the spectral parameter at fixed delta, the transfer matrices commute. And moreover, if this ratio is equal to the delta of XXZ, then they commute as well. And I kind of mentioned this as an exercise. But for example, one parameterization that you could take is where you take A of U to be the sinh of U plus eta, B of U the sinh of u and c of u actually independent of u, so just sinh of eta. And then you can compute that in this case, delta is the quash of eta. And of course, there's an overall normalization, which I removed here. Maybe we can call it rho that's inserted. Last time I called it r, but this time I want to keep r for something else, so let's call it rho. So this is one parameterization that clearly fixes delta, because we don't vary eta. But this is sometimes called, well, it's also an anisotropy parameter in some sense. So we have these two parameters in the overall normalization. So this is what we saw last time. And maybe I should actually, so delta larger or equal to 1, this just corresponds, can be parameterized by eta non-negative. Then delta between -1 and 1 can be parameterized by letting eta run, so we could call it I gamma maybe, and then we can let it run through the interval I from 0 to pi. And then if you have delta smaller, or equal to -1, we can take eta to take values into I pi plus some positive number. So if you plug this in the cosh, you see that it works. So in the complex plane, so we have the eta complex plane. We have this, and then this, and then this. So this value here corresponds to delta at 1. This value here, which is at I pi, corresponds to delta at -1. Here is delta going to -infinity, delta going to +infinity, and so we have this, what we call the axial, planar, and axial regimes. And of course, in this intermediate planar regime, it makes sense to instead use gamma, and then the sinh becomes normal, just a sign, and we can absorb the I in the rho, so which we get out of the sign. So we can always use a real parameterization by changing a little bit what we call, here we would also just replace, we would call this part gamma, and so on. Maybe. So you can always have a real parameterization, but we're naturally led to include complex values for our parameters. And so we note that this parameterization here, viewed as a function of u and eta, is actually entire in u and eta. Okay, so that's basically what we discussed last time, with a little bit more about this parameterization. Okay, so far, this part, this is like old school integrability, old school quantum integrability. And today we will make the passage to more fancy and modern versions of quantum integrability. This goes as follows. So the name of this part is called the quantum inverse scattering method. Which of course is way too long, so people usually just abbreviate it to the corresponding acronym. And the first little bit is about something called the R matrix, which is really the fundamental building block or piece for the quantum inverse scattering method. Okay, so we have our transfer matrix, which, by the way, now we think of it depending on u at fixed normalization of the vertex weights and at fixed value of delta. But we want to consider all the values of u at once. And we got this by slicing up the partition function into horizontal slices. So what we will now do is we will slice up the transfer matrix into vertical pieces to go even further down into more elementary building blocks. So what we then get is called the R matrix. And graphically, R of U, I will identify it with the following picture. Just a single vertex, but without fixed spins on the outside. And just like before, we're going to view this as an operator. And the operator is going to go from a copy of C2, which we attach to the horizontal line, times a copy of C2, which we attach to the vertical line, to itself. So 2 C2 attached to the horizontal line, and C2 attached to the vertical line. And this is just one of the little kind of annoying things that you have to get used to. So it's very important that here we have horizontal and vertical, and here we still have horizontal and vertical. So I'm going to put an exclamation mark here, because we will see this come back. This is kind of a potentially confusing point, so I want to make it more explicit. So let's, as always, go to its matrix elements. So then we have some, well, let me write. So we have an R prime, comma S prime, which I'm going to mark red because there may be, this is more subtle device. Then we have R of U, and then we have some R and S. And pictorially, this could just corresponds, well, we redraw a vertex. R is the value of the spin on the horizontal line. S, like before, is the spin on the vertical line. But now, remember, we want it to go to horizontal and vertical. So the R prime labels the spin on the horizontal line, and S prime the one on the vertical outgoing line. It's kind of, if you kind of think of it as going like this, here you start with R and then S, and here it's S and then R. And the reason is that we always want to order it as horizontal, comma vertical. Okay, so there's always this little kind of inversion in the thing. It's a little bit annoying, but it is what it is. In other words, we can actually compute the matrix. So I'm going to draw, well, make a 4x4 matrix, and I'm going to actually draw it. So it should be a rather big matrix because we're going to put vertices inside. And I need to order the bases. So the incoming lines are ordered as follows. They're dotted, dotted, and then leave some space, dotted, thick, then thick, dotted, and then thick, thick. Right? So this is just the basis of our C2 times C2, like we had before, and I order it by first horizontal and then vertical. So it's kind of the same basis as we had before, but now I draw them as some sort of angle, because that's what they do for the R matrix. But for the outgoing base, we have dotted and dotted with our arrows, but now we have thick going up and dotted horizontal, and then dotted going up, thick horizontal, and then the both thick. Okay, so this is just because of the because of this reversal there. So the important part is to be aware that these two, in some sense, look like they're kind of the wrong way around compared to this, but not if you remember that we want to order horizontal and then vertical. Okay, so this is the 4x4 matrix. So now I can draw the vertices. So at the 1, 1 entry, we have this completely dotted vertex. At the 2, 2 entry, we have this vertex. Here we have, this vertex. Here we have this vertex. So now I'm just combining the incoming and the outgoing pictures, and I'm only drawing those for which the weights will be non-zero. So we have zeros everywhere else. Okay. Now we recall that we identified the pictures with their weights. So now we can say that this is just a 4 by 4 matrix with A of u in the top left, then next diagonal entry B of u, below it and to the right of it C of u, in the other corner of this 2 by 2 block B of u again, and then A of u in the last diagonal entry, and zeros everywhere else. Just to make completely sure that we are all happy with this space here has bases ordered as first with plus plus, then we have plus minus, then we have minus plus, then we have minus minus, and we recall that the first one is horizontal and the second one is vertical. Horizontal and vertical. So that's all I've done. But I've implemented this correctly in terms of the pictures. Like that. Okay, so this reversal sounds complicated. It's just we have to remember. Maybe I should also mention that we identify the plus vector with spin up and the minus vector with spin down. Those are identification in terms of the x-axis. Okay, so here's this R matrix. Now let's do some computation like before. So what we're going to do is we're going to draw two vertices next to each other. And we're going to fix all the possible spins. So we have R to the left, R prime to the right, S1 and S2 below, and S1 prime and S2 prime on the top. Of course, among all the vertical edges, I'm just labeling from left to right, like we did. So by, and let's actually call it R double prime. Because by our summation convention for the internal line, we know that this is the sum over all the R primes equal to plus or minus. And then we break up the picture into two pictures. And then we have an R to the left, R prime in the middle, R double prime to the right, S1, S2, S1 prime, S2 prime. So that's the sum over R prime. Now we recognize that these are just the matrix entries of our R matrix. So let's write it down. We have R double prime, S2 prime, R of u. Then R prime S2, and then the other entry is R prime S1 prime, R of u, R S1, like that. So now we're going to do the same as last time. Remember that last time what we did is we recognized that the sum over R prime, and then here we have the ket and the bra of R prime. That's actually just an identity matrix. So we can remove it. So in other words, what we're going to get, and now, well, let me first write it in intermediate step. So we can also think of this as the following matrix entry. We have R double prime, then S1 prime, S2 prime. So this is kind of the matrix entry. Then we have an R of u. We only have a single R prime ket, then a single R prime bra, then R of u, capital, the R matrix, and then last R S1, S2. And now I need to specify what all of this was. So this guy is horizontal, these two are vertical, this here are both horizontal, this here is horizontal, and these are vertical. Okay, but now we see a little bit more explicit that we just have this sum over R prime, and we have this components of the identity matrix in there. So in other words, this is just the same as the entry R double prime, S1 prime, S2 prime, and then R of u, and then a product within the horizontal direction. So let me just call it dots with a horizontal subscript. The other R matrix, and then R S1, S2.
Yeah, the two R's act on different.
Exactly. So this notation is of course a little bit annoying. So we're going to improve our notation a little bit. And this goes as follows. I'm going to put it there. All right. Okay. Okay, so indeed, so we should kind of refine our notation a little bit because this is a very awkward notation. So what we'll do, and I was actually secretly already doing it before, but I shouldn't have, is I'm going to label the spaces. Because we have lots and lots of copies of C2, so it's kind of good to keep track of which copies of C2 everything was. So in pictures, what I will do is, our pictures, they always have the following form. There's some stuff, and then there might be some line coming in like this, there might be some lines coming in like that, and then there's some lines going out in both directions as well. So what I will do is I will call this horizontal space 0, and then these 1 up to L. And the outgoing spaces are labeled in the same way, but we keep track that we first label the horizontal space by 0, and then the vertical spaces 1 to L. And to such labeled spaces, we associate a vector space, which is C0, the horizontal vector space, and then we have C1 copies of C2, sorry, C2 copies L. And this part here is just our Hilbert space from before. And then such a picture can be viewed as an operator from this tensor product to this tensor product. Now this first copy is usually called the auxiliary space. Auxiliary space. And this last one is called the quantum space. And the reason is that this H is just the Hilbert space of the spin chain, which is a quantum mechanical model. So this is the Hilbert space for H delta, the XXZ Hamiltonian. And this one is extra. This space is extra, so it's a help space from the spin chain point of view. So that's why it's called auxiliary space. And I'm just going to emphasize one more time, always ordered horizontal tensor product vertical. In other words, in these type of pictures, the spaces, these local vector spaces, follow the lines. Right? So I'm just thinking of this as a line which carries G auxiliary space all the way through. And here's a line that labels the first quantum space, the second quantum space, and so on until you get the full global quantum space. And each of these lines kind of carry a vector space, a copy of C2. So with lots of copies of C2. And now what we will do is we will indicate the spaces as subscripts on our operators. So I now have an R matrix, which has a horizontal line, so a copy of this auxiliary space, and then some vertical line, so let's call it the little ELF line. And then it's the picture where the 0th line crosses the ELF line, like that. And now we can go back to our computation. So let me add in maybe orange some extra stuff. Here's our 0th line. Here's our first line. Here's our second line. Here's our 0th line. Here's our first line. Here's our 0th line. Here's the second line. Then this, if you wish, so this is the R matrix. Well, this picture corresponds to this crossing here. This crossing here. So it's the R matrix, which is acting at the 0 and the second line. So I give it subscripts R0, 2. Oh, and here, of course, I should have also indicated the spectral parameter. Like that. Then this one is an R matrix 0, 1. And if you wish, what you could do is you could say that these are the vectors 0, 2, 0, 2, 0, 1, 0, 1. To remember for all the vectors and so on, where they live in the picture. And in the middle line, we still have an R02 and then an R01. This horizontal one is a vector which is just in an auxiliary space only, this little bit there. Whereas here, on the left and the right, we have 0, 1, 2. 0, 1, 2. And then finally, here, we have the matrix element with respect to the 0, 1, 2 tensor product, 0, 1, 2. And then here we have an R02 and an R01. And the product is automatically horizontal because we have the 0 appearing twice. So we understand that this guy acts first, it acts in the 0th and the first space. Then this one acts, it acts in the 0th and the second space. So they have a product in the horizontal space. So that's what these subscripts now nicely account for. In other words, if we just draw the picture without taking all these entries, this picture 0, 1, 2 corresponds to R matrix 0, 2 of U, R matrix 0, 1 of U. That's what we check, component by component. And the reason that I was very careful to write my order of my vertices like this, which is kind of opposite to the picture there, is that here we note that R01 of U acts first, right? Because we put a vector on the right, then first this R matrix X, and then that R matrix X. And in terms of the graphical notation, that is precisely what these orientations of the lines that I've been insisting all along take care of, because we just know that the orientation of the lines tell us which R matrix X first and which one X next, and so on. So this can be read off the orientation of the lines. We just move backward. Over pieces later. You get. So now we can do it similarly. Let me just draw this picture. So we have this horizontal line, and now we're going to cross all L of our vertical lines. 1 all the way up to L. And this corresponds to a product of R matrices, R0L acting last, all the way down to R01. And since the zeros are repeated, we understand that the products of these R matrices are in the horizontal space. And of course, there's a little exercise is to actually check these in components. Check entry-wise. Very good. So now we want to go towards the transfer matrix. Here I will do the exercise myself. So let's take an entry. some L tuple of S primes, then our transfer matrix depending on U, and then another L tuple of S's. So pictorially, this now corresponds to one line like this, L lines like this, and we give them 1 up to SL, and S1 prime to SL prime. These were the components, the matrix entries of our transfer matrix. So now what we're going to do, of course, is we're going to understand that, well, the only thing that we don't really haven't seen yet is this horizontal boundary condition. So let's use our summation rule to say that this is a sum over R. Then we have the zeroth space with spin R here. 1 up to L, spin 1 up to spin L, spin 1 prime, spin L prime, and then here we have the same R. But here we have a component of something that we basically have computed here, or I told you the answer of. So what this is the sum over R, and then the component R S prime, this product of R matrices, R0L of U all the way down to R01 of U, and then R S. And here I can again label that this is the 0, and then 1 all the way up to L, 0, 1 all the way up to L. So if we focus on the 0 part, we see that we now again have a trace, summing over all the diagonal entries in the 0th space. So in other words, what this is the S prime component of the trace over the 0th space of this product of R matrices, R0L all the way down to R01. And then it's spin S there. In other words, see that the transfer matrix, which was a picture that, is just the trace over the auxiliary space of a product of R matrices concatenated in the horizontal direction. Of course, this result should not be surprising because what I repeated, I literally repeated the story that we did for the partition, where I first defined a single row, then I checked what happens for products of these rows, we put them on top of each other, and then finally we had to take the trace for the boundary conditions. So here it's exactly the same. We have, in this case, horizontal product and then horizontal boundary conditions. So let me tell you a little bit more formally what's happening in terms of these subscripts. So in terms of operators, these subscripts denote the factors of our big space, C0, C2, the 0th component, and then let's say tensor L, on which for example, the R matrix X. By the way, maybe I should say that for full consistency, one should put all these labels 1 up to L on the transfer matrix, because that's the spaces on which it hangs. But often we show all the subscripts except for the one that corresponds to the full Hilbert space. This is kind of this is understood. Because it's just so many things act on the full Hilbert space that we don't write it anymore. So we write it if it's just a few spaces, and we write the auxiliary space, but we omit the full Hilbert space. And it should act non-trivially, so not by the identity. Non-trivially. And this is just like what we did for the entries which I called HLL plus 1 in the formula for the spin plane boson. So it's just the same convention. But the difference is that here those subscripts were always adjacent, and in this case they are not adjacent. So if you want to put this in the computer, what you do is the following. You write your R matrix in terms of some coefficient functions, let's say R alpha beta of U, and then some sigma alpha tensor sigma beta. And I denote sigma 0, let's say this identity. Then we have our sigma plus and minus, and then we have sigma z. So together, these four matrices form a basis for the all 2 by 2 matrices. So I can decompose an operator on just a copy of C2 in terms of these four matrices. Here I have 2 copies of C2, so I just take a pair of these type of matrices, and then I have some coefficient functions, alpha and beta. And what we do from this is then R0L of U is, well, it's a sum with the same coefficient functions R alpha beta. Then we have our sigma alpha in the 0th space. Then we have lots of identities, little l minus 1 of them. These take care of spaces 1 and so on. Then we have our sigma beta in space little l. And then we have lots more identities everywhere else. Like that. And if you like even more formally, this is a little aside for those like this kind of stuff. These subscripts they denote embeddings of operators, let's say in this case on C2 and C2 for the R matrix, on all the operators on our huge copy of C2 0 tensor the Hilbert space. So we just take a 4 by 4 matrix and we let it act on our huge vector space with auxiliary space and the full spin chain Hilbert space. And we act trivially by the identity almost everywhere. And the subscripts say on which vectors we do not. If on which vectors we say act non-trivially. And then finally, the remark is that trace over 0 is sometimes called partial trace over the auxiliary space. And if you want to do this formally, you can say that operators on this huge space, C2 tensor the Hilbert space, C2 0 tensor the Hilbert space, is actually the same as operators on C2, the auxiliary space, like this, tensored with operators on the Hilbert space. And then we can take a trace on this component and just do nothing on this component. And that's how we define the partial trace. A little bit formally, but the graphical notation takes care of all these kind of formalities. So if you don't like the formalities, the pictures, they account for everything that we need to know. Are there any questions at this point?
Embedding, you mean injection?
Yeah, like an injected. So now this technology will allow us to finally answer Antoine's question: how do we get from the 6-vertex model to the XXZ spin chain? So this goes as follows. So recall, we have these things which are called trace identities. I don't think I mentioned this word last time. which say that the case Hamiltonian, a case Hamiltonian can be defined as a case derivative at some special value, u star, of the logarithm, traditionally, of the transfer matrix. And then all these operators are guaranteed to commute with each other and with the xxz Hamiltonian at the same value of delta. They commute and also with h delta. So let's actually compute some of these Hamiltonians. So we need to first choose a suitable special point, u0, u star. We want to make this R matrix. So now our transfer matrix consists of a product of R matrices. We want to choose our u star so that the R matrix is maximally simple. So with the above parameterization, this R of u, it is actually given by rho times a matrix with entries sinh u plus eta, sinh u, sinh eta off diagonal, another sinh u the diagonal, and then sinh u plus eta in the last diagonal entry. Eta is fixed. That's right, my u's and my etas are a little bit general. Eta is fixed, so we're not allowed to do anything with eta. So the simplest choice is, well, we can take u star equal to 0. Because then we kill some of these entries and the remaining entries all become equal. So what do we get there? Well, let's say we had our R0L, oh, and now u is 0, u star is 0. So what does it become? It just becomes rho times sinh eta, and then times the permutation operator for 0L, where this permutation operator is the following 4x4 matrix. It's 1, 0, 1, 1, 0, and then 1. So we can check, right? These diagonal entries, they vanish, and here we get the same as there. So we get this matrix times our rho sinh eta. And this is the permutation matrix. You can check that on a basis, it means P of S1, S2 is equal to S2, S1. So the two spins are swapped. This is the spin permutation. Of course, we can also draw this relation. So actually what I will do is, so let's just to avoid some factors floating around, so let's pick rho to be 1 over sinh u. Sinh eta, sorry. Then I don't have to take along all these factors, these prefactors. Then I can draw, well, I have my crossing the R matrix, the 0th and the 11th line. I take parameter u to be equal to our special value 0, and then it's supposed to become the identity. How do we draw the identity? The permutation. How do we draw that? Well, we just draw this. Right? This is the vector that goes in here is kind of carried up, and the vector that goes there is carried to the right. So what you see is that the vectors graphically kind of this nicely accounts for the fact that horizontal and vertical spaces are swapped. Of course, in this case, we have to be kind of careful that really the auxiliary space, maybe I should draw it with my orange marker. Even though I draw it like this, in this case, this is maybe a little exception to the rule that the space is supposed to follow the lines. They're still going from horizontal to horizontal. And also note, because we need to compute traces over the auxiliary space. So for instance, if we have the trace over the auxiliary space of this permutation, then graphically what I do, well, it should look like this. So what happens is you just have a line coming in, it goes to the right, it just kind of wraps around the cylinder, and then it goes straight on. But nothing happens to this line. So this is just a single line like this, which is the identity on our space L. We usually don't indicate subscripts for identities, but let me do it here. Graphically, this is kind of clear. If you don't believe me, check this with formulas. So compute these partial traits with formulas. Only going to rate it. All right, so now let's compute some conserved charges. So some of these HKs. And actually, I will not directly use this formula, but I will just do I will rediscover this formula instead. So first, we start from our transfer matrix, and let's just plug in our special value U star. So pictorially, we have our transfer matrix. And we have to plug in U is 0. So this rule, this diagrammatic version just says that we have to open up all these lines there. So what we're going to get is this picture. And the nice thing is that the graphical notation already computed the trace over the auxiliary space for us, just like it did here. The zeroth space has disappeared, we just have L lines like that, and we can easily see what it does. It just takes a spin configuration and it shifts it cyclically one to the right. In other words, this is our G inverse, because my G, I think I defined it to be the left translation operator for the spin chain. So here instead we get the right translation. Operator. Now recall that translation operator had eigenvalues e to the I p total, the total momentum. So if we would take the logarithm of our transfer matrix at our special value, then we just get minus I times the total momentum operator. Which indeed is one of our conserved charges. Of course, the explicit expression of taking this logarithm is not so insightful. It's much easier to work with G or G inverse. But the physical interpretation is very clear. If we take the logarithm, we get not the shift operator, but just the momentum. And then there's an exercise just like this here. So check this with formulas. And match the steps. So the point is that this graphical notation is really in one-to-one correspondence with formulas. And if there's some sort of different ways to interpret the pictures in terms of formulas, then those two things, expressions that you get, are equal in formulas. So it's really extremely efficient way of doing it. And this exercise is write down everything in terms of R matrices, use this this thing here, work with permutations, blah, 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 actually compute the trace, and so on. And you will see that what you do is you write like half a page, and some of the steps in there are trivial in terms of formulas. Basically, this step here is a lot of work, but you can see that it really works. So it's useful to do. If you are not convinced about the pictures, then just compute and see that the pictures do everything for you. So this is the first conserved quantity, which is good. Last time we observed that the transfer matrix commutes with the shift operator. Now we see that it in effect contains the shift operator if we think of all our transfer matrices with the same value delta at the same time, simultaneously, so that we can vary this fractional parameter. So now, okay, let's do the next thing. So we're going to compute the derivative of the transfer matrix. So this is, of course, going to involve R prime 0L of U. So I need to give some graphical notation for it, and I will denote it by an R matrix marked by a dot. And the dot tells us that that's the R matrix whose derivative we're computing. And in fact, we'll of course get the R matrix, this derivative at U is 0. So let me just say that this picture already accounts for the U is 0 as well, because otherwise I will need to write it by hand all the time. So then, well, we have some products of R matrices and then a trace. So if we take a derivative, we're going to get a sum. Quite like this rule. We draw our same picture. This, and then one of these lines we have our derivative. Something like this, and then we still have to evaluate everything at our special values. Now I can again open up all these lines because we're at U is 0, so let's just do that. And in fact, we notice that this trace in the horizontal direction means that we can actually, well, let me write it like this. L is 0 to L, and then we get this picture where these are opened, these are opened, these are opened. Sorry, this one is not opened. Here we get the dot. So this is what it looks like. So we see that basically it looks a lot like this picture, except that we have a sum of them, and for each one of them, each of these terms, one of the entries, one of the vertices has not opened up, but instead we took a derivative. Now, actually note that here in my picture, you see that this picture, L might be, the little l might be equal to big L, in which case this line kind of goes around periodically like that. So in fact, this sum I can also write as a sum, just a cyclic sum, like before. Is automatically baked into the graphical notation. Now we also note that, as I said, this part here, it really looks a lot like this here. So actually, let's try to undo almost everything that's happening here by just multiplying by the translation operator. In other words, what I'm going to compute is the logarithmic derivative at our special point of the transfer matrix, because the logarithmic derivative is just the P0 inverse P prime, where the logarithm, of course, throughout is, it's a logarithm of a matrix. So you use the power series for logarithm, and then you plug in the matrix. And this identity is true. It uses that all these guys in here, they commute nicely, of course. So, right. So everything works well when you take the derivative here. And so pictorially, what's happening? Well, we have our cyclic sum over little else. And then I'm just going to take this picture, and then after it, I'm going to apply this. So on top, I'm going to put the inverse of this picture. Well, what is that? Let me just draw it for you. You get this line coming in from the left, going up, and then going out to the right. We get a line bending to the right, and then going up, and then bending to the left, and up again. Then we get this special vertex. And then otherwise, we just get this stuff here, where now I drew on top a translation operator, which shifts one to the left. Right, so this part here is just G, which is P0 inverse. So now we see many lines which temporarily move to the right, and then they move back to the left, but they don't do anything else. They don't touch any other lines, so they're just identities. In other words, I can straighten those lines. I get the sum over all my cyclic phi, And then I just get lots of straight lines going up. And then at some point, I'm going to get this little picture here. This was my L, like that. So again, notice that the trace over the auxiliary space is computed completely easily using the graphic notation. Actually, let me write this, copy this here, and I can write one more line below. So now we need to just know what this derivative actually was. So here we have that our single picture that looks like that, with the dot in the middle. Well, if you do all the formulas carefully, you see that this is the permutation times the R matrix, the derivative at 0. This is a 4x4 matrix, and we can compute its entries. Let me again write the basis on top. So incoming, we have dotted, 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 full, full, dotted, full, full, and outgoing we have dotted, 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 full, full, dotted, full, full. So the reason why I draw this again is that we have a permutation here, which kind of swaps the vectors one more time. So in this case, the order left to right is kind of preserved between the incoming and the outgoing, basically, because of this permutation in here. And the permutation came because it's this permutation there. So if we actually check what this is, well, we get delta, which was our cosh of u. Then we get 0, 1, 1, 0, delta. And then we had the times row if you wish. Actually, it occurs indeed. In other words, with our conventions, this is 1 over the sin of u, eta, because that's the value that we chose for a row. And then delta times the identity tensor the identity, so just the diagonal matrix, plus, and then our little h delta of the xz Hamiltonian. Remember, it was 0 minus delta 1, 1 minus delta 0. So up to some multiple of the identity, we recover our local Hamiltonian, the sum ends of the xz spin chain Hamiltonian. So before I write down the result, the exercises again, check this using formulas and match the steps. But especially in this case, I think that the graphical notation is way easier because it really takes nicely account of all the kind of gymnastics that you have to do with permutations. In other words, so the conclusion is that if you take 1 over rho, if I reinsert my rho, logarithmic derivative at our special points of the transfer matrix, and what you're going to get is a sum over all our cyclic ordered sides, and then we have delta times the identity minus h L plus 1. I just shifted summation. Well, we got L minus 1 from L. And this is just L delta times the identity. I think I did plus here. Minus our xz Hamiltonian, h delta. So this is our first important result today. now it makes sense that the XXZ Hamiltonian should commute with this X-vertex transfer matrix at the same value of delta, because the X-vertex transfer matrix actually generates the Hamiltonian. It contains the Hamiltonian. So before we take the break, let me just go back to this phase diagram that we had of the 6-vertex model. We had our A over C, B over C, we had our special values 1, 0, 1, maybe straight lines from 1 to 1, and they're going like that. These were delta is 1, delta is 1, delta minus 1. Then there were lots more lines, like this. They start getting closer and closer to this axis. At some point, actually, they collapse onto this axis here, like that, which is delta is minus infinity. Here we have the circle, for instance, and then we get kind of more like parabola type shapes until we get to delta is 1. And then here, it kind of looks like this. Last time I wasn't completely sure, but they just interpolate between the straight line and this axis here. It arises as delta going to plus infinity in this one too. So this was our phase diagram of the 6-vertex model. So what we've done is we computed the derivative at this special point u is 0. So at u is 0, do I still have my here? At u is 0, the a coefficient just becomes 1. The b coefficient becomes 0, and the c coefficient also becomes, well, actually the a becomes equal to the c, and the b vanishes. In other words, the point that we're computing at is this point here. And we see that at this point here, indeed, all the lines going from minus infinity all the way up to infinity, they touch that point. And the spectral parameter, what it does is it parameterizes as you go away from this point in all the possible directions. That's what's parameterized by u. So we can fix our delta. We start from this point, then we fix our delta. This gives one of those, select one of those orange lines, and then the spectral parameter parameterizes this entire line. And what we've done is we've computed the derivative of the transfer matrix in this direction. So the Hamiltonian kind of generates is the infinitesimal generator for the kind of the translations, the movement away from this special point of the transfer matrix. So that's kind of, in some sense, what the Hamiltonian does. In other words, the Hamiltonian, you can kind of think of it as u as kind of like a time, plays the role of time, and then it's really the infinitesimal generator of the transfer matrix. And of course, it does so at a fixed value of delta. And we start from this special.
Think of it as changing slightly the values of A and B and C, so the way in the 6-vertex model.
Yes. Exactly. So what you do is over here, there's kind of like tangent spaces parameterized by values of delta. The direction is parameterized by the value of delta. And you can move along one of these tangent lines, and then the Hamiltonian is the infinitesimal generator of the transfer matrix along that line.
So physically, it means that it's because the 6-vertex model is solvable in or integrable in for any values of ABC that you can move always.
Exactly. So you pick your values for ABC. It corresponds up to normalization, which we don't care about, to a single point in here. Then this single point will always be connected via some orange line to this dot here, except maybe when we're here, but then we can use some symmetry to end up at this side. I mean, we kind of saw that this reflection is more trivial. Alternatively, of course, you can do the same expansion here. So you will move along your orange line from your initial points to here, and all the transfer matrices attached to any of these points all commute with each other. And that's what we use, but mostly related to these.
Here we were lucky to find one point where all the lines meet.
Mm-hmm.
It's a bunch of lines that meet at one.
If that would happen, it would mean that your R matrix would have different inequivalent values of the spectral parameter at which they simplify. I guess that I cannot rule out. In the examples that I know, it doesn't happen. The situation is always like this. I mean, here, in some sense, right? This is a model which is not quite connected to that one here. But in terms of the XXZ spin chain, this kind of fan is already enough because we just need to know about all the values of delta. And this here is just related to, it's one of these symmetries that if we, I don't know, how do we exchange A and B? By swapping horizontal or vertically only the thick and the dotted lines. In terms of pictures, it doesn't matter much. Here I should emphasize maybe more that now this order is because of this permutation. Are there any other questions? If not, we can have we could also do online questions, I guess. Okay. Very good. So now we're going to go to the next part, which is called 5.3 I'm counting, which is called Young-Baxter integrability. Well, quantum integrability, but that's clear if it's a Young-Baxter. So what we want to do is we now use our transfer matrix. We built it from our matrices, and we use the transfer matrix to really make the connection to the XXZ spin chain. But what we now want to do is we want to rederive the condition of having commuting transfer matrices from this local setting. So we're going to consider our transfer matrix of U, which is equal to this picture. And we also have a second transfer matrix, so T of U prime. And it will be convenient to use a separate label for the auxiliary space here. So I will call it 0 prime. It looks exactly the same as the other one. Of course, this is a space that we eventually trace over, so it doesn't matter what we call it. It's just some sort of internal thing. But so in other words, we have a second auxiliary space T2 0 prime. Where's this guy here? Auxiliary space T2 0. So this will be convenient. So as we've just seen, commuting transfer matrices, they imply that we have lots of conserved charges. Lots of conserved. So actually another exercise could have been computed the second logarithmic derivative. You can also do it graphically and can compute the second conserved charge. And you will see that they become slightly less local. So the higher you go, the more sides, nearest neighbor sides will interact. So these lots of commuting charges, you can think of this as some sort of macroscopic version of being quantum integrable. So it's kind of like a macroscopic quantum integrability. So in other words, we could say a model is macroscopically quantum integrable if it has lots of conserved charges, so lots of commuting operators. But then we have to make precise what we mean by lots. So maybe it's a maximal abelian algebra of all the possible operators on the Hilbert space. But there's a kind of a very clean, more minimal, well, not more minimal, but more simpler kind of building block, which is a sufficient condition. And this is called Young-Baxter integrability. quantum integrability. And this is a microscopic version, as will become clear in a moment, of quantum integrability. So that's the idea. We'll just remove all of this. Maybe keep our nice formula. So the claim or theorem is the following. Suppose there exists, and this is, let's say, an auxiliary R matrix which I will denote by R0, 0 prime, and it depends on U and on U prime in some way. So it has two arguments. So it looks like an R matrix, but it's different because it has two arguments. And I will draw it as two lines crossing, 0 coming from the top in this way. So 0 and 0 prime. I guess you get the drill. What we're going to do is we're going to view this as an operator from C2, 0, tensor C2, 0 prime to itself. C2, 0, C2, 0 prime. And we are careful that we take into account that 0 came before 0 prime. So it's kind of, it looks like a rotated version of our R matrices, but the labels tell us that it's a bit different because it has two kind of auxiliary spaces. And also it depends on two different parameters. And of course we can also take entries just to do everything which is explicit. So that R1 prime, R2 prime, R0, 0 prime, U prime, R1, R2. Entry corresponds to the picture where we fix our R1 spin in the 0 incoming space, our R2 in the 0 prime incoming space, and then we have R2 prime and R1 prime ordered like that. And so usually I don't indicate it, the 0th space goes out there, and the 0 prime at the top, and 0 at the bottom, because the spaces follow the straight line. Okay, so assume that we have such an operator with the following properties. So such that two things. Firstly, it should be generically invertible. In other words, it should be true for almost all values of U and U prime. We should have that there exists some inverse, which I will call R0, 0 prime of U, U prime inverse. Graphically, I will draw it. It looks just like before, but now 0 prime is at the top and 0 is at the bottom. Let me color these lines just to kind of, so this coloring has nothing to do with the spins, but just to kind of, we have a 0 and a 0 prime. So let's say the 0 is this blue line and 0 prime is the red line, like that. And this guy looks similar, but the other way around. And this notation is kind of good, because now we understand that if we have a picture like this, well, being inverse means that this is 0 prime at the top, 0 at the bottom. This is just the same as this picture. In other words, if we have in equations, this is R0, 0 prime, U prime, acting after R0 prime, well, 0, 0 prime, U prime inverse, and it should be the identity. And of course, we have another picture that says the same, but with red inverted, reversed, which is the same relation for the opposite one. Okay, so we want for almost all values of u and u prime such a invertible matrix to exist, and the really important property is number 2, which is called the Yang-Baxter equation. Which we always abbreviate to YBE. And write the formulas and draw it. So the formula is for R 0, 0 prime, U, U prime, then R 0 L of U, R 0 prime L of U prime. So we have this formulae. This is the following. We have this line, and that line, and we called them 0 prime, 0 prime. Let me check. Oh shit! I messed up, of course. It's this because I would like this to be perfect. I want this R matrix over here. There we go. And now, graphically, the rule is quite clear, this equation. It just says that we can move this white line through the crossing of the two other ones. It's also the same, this picture. Where on the outside, the spaces are ordered in exactly the same way. With 0, 0 prime L, and 0, 0 prime L. Here as well, 0, 0 prime L, 0, 0 prime L. But the details in the middle look a bit different. So we have two different pictures which are equal. This one we can convert again into operators. It is R0 prime L of U prime, then R0 L of U, and then our R0, 0 prime U comma U prime.
When you look at the picture, how do you know that how do you, so I see you do first 0 prime L on the picture, but then why do you do first 0 L and afterwards 0, 0 prime and not the other way around?
So in this picture, okay, so let's look at this picture. So the first operator to act here, well, the orientations tell us in which order to do things, right? So this one here, it is the closest to the endpoints of all the lines, right? This one is also close to an endpoint, but one of the lines is not an endpoint and the other one is. So this one is going to act last. So it means that on the left, we should write our R0, 0 prime, because that's this picture. Then this picture acts before that. So this is the 0L, which is this guy here. And then finally, we have the red comma white, which is our 0 prime L. Likewise, in this picture, we have red white as last, so our 0 prime L. Then we get our blue white, which is our 0L. And then we get our blue red, which is our 0, 0 prime. So the picture really contains precisely the order of all the operators that we want to take into account. Does that answer the question?
Yes, thanks.
Okay. Very good, because this is an important point. So far, the order was kind of clear, but now we're getting a bit more complicated picture. So it's good to make sure that we understand that the order is precisely contained in the picture. Okay, so what is the statement? If we have such an R matrix, which is generically invertible and obeys the Yang-Baxter equation, then the corresponding transfer matrices T of U and T of U prime commute. And for those who are not quite convinced yet, there's a little exercise, which is that check entry-wise that indeed these diagrams correspond to the formula. diagram corresponds to equal. And you'll see by writing using summation convention on the internal lines and blah blah blah, you will see that these products are precisely in that. Okay, so our local conventions, our microscopic or local conditions are this generic invertibility and our Young-Baxter equation, and there are just some conditions on these R matrices that we have for the two transfer matrices together with this new auxiliary R matrix which we want to exist. And the proof is very simple. The proof is called the train argument. I guess it should really be called the railway or the rails argument. And it goes as follows. So consider the product T of U prime. So graphically, my U prime is red and my U is blue. In terms of pictures, of course, what this means is we have lots of these lines, like that, and then we have our zero prime here, and our zero here. So let's use our first condition. Assume that we're at one of these generic points. We'll get there in a moment. So what we can do is we can just insert, we can replace the straight lines on top of each other by such a picture. So what it will look like is we have our 0, then we have our straight line going through all of those, and then we're just going to cross it like this. Our 0 prime, and we go straight, cross, and back, and like that. And then we have all our other lines. Very good. So let me emphasize that at this point, 0 prime is temporarily on top, and 0 is on the bottom, which is good because we want to swap the two colors of the lines. Now, of course, we notice that here, this little picture, if we zoom in on this part here, that is precisely the picture that we have here. So we can use our Young-Baxter equation to move one of these white lines from property 2. We can redraw the picture, but now 0 is horizontal, then it's going to go down, and then horizontal a little bit longer, and then go up again. 0 prime, like that. So this is 0 prime, 0 prime, 0, 0. And then here we have L-1 lines, and the Lth line is now moved to the region where the red is on top of the blue. And clearly we can, here again we have the same picture that we had before. So we can just keep repeating this argument using 2 several times until we move all of the vertical lines through. So then the picture is as follows. We have blue briefly on top, then it goes down, it stays at the bottom very long, and then it goes up again. And red does the opposite. Like that. This one are 0 prime, this one are 0. And now all our L lines are in the region where red is on top. But now remember that we have periodic boundary conditions. With this picture, we can kind of rotate it a little bit, and it is the same. In other words, this picture is exactly the same as if I would have red starting at the top with 0 prime, all the way, then briefly to the bottom, and then ending at the top. And blue doing the opposite. with our L lines still sitting on the left. So the only thing I've done here is I've just rotated this picture a tiny bit in cyclically to the left, so that this leftmost crossing is now sitting rightmost. If you would do this in terms of equations, you would use the cyclic property of the trace here to do this. For us, it's just the periodicity of the picture, the horizontal periodic boundary condition. And then finally, of course, we know that we can just use our invertibility condition. Now 0 prime is at the top, 0 is at the bottom, and we just have our L lines like this. And this is just our transfer matrix now of U prime acting after one of U.
What if we are U or U prime such that there is no inverse?
Great. So now this is the argument that shows. So what have we shown so far? Right here. What we've shown is that T of U and T of U prime commute almost everywhere, almost always. However, now we use an extra property which I didn't state explicitly here, but these are parameterization. So parameterization of our ABC, of our vertex weights, A of U, B of U, C of U, was entire. So what this means is that the entries of the transfer matrix are polynomials of degree L in an entire function, so they are also entire. So the entries of the transfer matrix are also entire in U. So it means that we have commutativity almost everywhere, except for some sort of measure 0 set. The operators here, and therefore also this whole thing viewed as a function of U and U prime, is entire. So what we can, so what this implies is that actually this commutativity, basically by continuity, by smoothness, it is true everywhere. So with this little box going here, our proof is done. Given those conditions, and using that there exists an entire parameterization of the transfer matrix, of the vertex, which we saw before.
Would this fail if the spectral curve was singular or something?
I don't know examples where this fails, but I cannot say that you can't come up with one where it does. Of course, the important thing is that almost everywhere this.
Yeah.
If you can come up with an example which is invertible away from a kind of on a set which is not invertible on a set which is larger than measure 0, then of course I cannot get inside that set. Yeah. Okay, so let's keep this. Okay, so a little exercise for those who do not believe is check all of this with formulas and match the steps. And one thing that's useful, so the point is that these formulas, right, there are lots of R matrices. So for instance, at some point, here you get this R matrix and these R matrix. And graphically, it's completely, we see that they act on different spaces, right? So it means that in the product somewhere, we have an R, 0 prime, maybe L minus 1, and then an R, 0, L. So their subscripts are completely disjoint. So it means that these two R matrices commute. R, 0, L, R, 0 prime, L minus 1. But you see, in equations, I have to write down. I have to move one through the other. Whereas graphically, it kind of means, you know, if I think of my time as kind of going a bit more like that or a bit more like that in some sense. So the pictures completely take care of all these kind of obvious commutativities. But if you have to write down all the factors of the R matrices inside all the transfer matrices, then, you know, this is already 2 lines of your computation. It's a lot of writing. And the picture, there's no, it's automatic. So the pictures are way better. But if you don't believe me, just practice until you do. Okay, so what is still to do? Well, we need to check that for the given delta and u and u prime and overall normalizations that I don't care about, we need to show that such an auxiliary R matrix R0, 0 prime actually exists. Now looking at this Young-Baxter equation, a note. So first we will look at the Young-Baxter equation, and then invertibility we will check at the end that it works. So the Young-Baxter equation, well, it contains, so this is an identity between operators on 3 copies of C2. Okay, so it's an identity between 8 by 8 matrices. So it contains 8 times 8 with 64 different equations for the vertex weights. For the entries, which I will denote, well, the entries of our auxiliary R matrix, and with given, let's say, A, B, C, and A prime, B prime, C. That's the entries of the 2 R matrices that we have, the one with delta and U and the one with delta and U prime, by ABC and ABC prime, A prime, B prime, C prime. So there are lots of equations to solve. Polynomial equations in all the entries, but still, lots of them. So I'll just briefly outline how it works. So one thing that is kind of an ansatz, so let's say assuming that our auxiliary R matrix, R0, 0 prime, well, let's say, assuming the ice rule and this zero fields business. In other words, assuming that our R0, 0 prime of U prime is itself of 6 vertex form with some coefficients A double prime, B double prime, C double prime, C double prime, B double prime, A double prime. Right, so here I use the 6 vertex form to only have 6 non-zero entries, and the zero field says that the A plus and the A minus are the same, the B plus and the B minus are the same, and the C plus and the C minus are the same. Assuming this is quite reasonable, all our given data has this form, so let's assume that the solution might also have this form. One can show that the Young-Baxter equation reduces to only 3 non-trivial, so some of the entries are automatically, they're just literal equalities, and nothing to solve. And then there are a number of non-trivial equalities, but you can use the symmetries of these type of R matrices. Right, there are 2 types of A vertices which are the same, but they can occur in different components of the. If you would have a non-zero field story, then they would be really different equations. But using these type of symmetries, we get only 3 non-trivial equations. So exercise. Use zero field and symmetry of the pictures. To show this, or to check this. So maybe let me give you one example, just to understand what we're really doing. For instance, there's an equality A B prime C double prime plus C B prime B double prime, which corresponds to the following picture. It's equal to the picture. Well, we have our Young-Baxter equation, but with external boundaries as follows. Here's an incoming thick line. Here's an incoming dotted line. Here's the incoming thick line. And outgoing from left to right are thick. Okay. So you can check that this is an equality. But then by the Young-Baxter equation, I can now draw the other side of the Young-Baxter equation with the same external boundary conditions. So incoming thick from left to right, thick, dotted, thick, and outgoing from left to right, thick, thick, dotted. And you can check that this is equal to B A prime C double prime. So here's an example of such a non-trivial equation that you get. But this is an example of one of them. And the other ones I will give but not draw. Or maybe I should draw and not give, or maybe I should just do both. No, let's actually just, let me just give all of them. So not just, for example, so it kind of helps with the exercise, and the exercise still works. So the next one is similar, but the primes are the other way around. So there's A, then C prime, B double prime, plus C, B prime, C double prime. So the picture, of course, is similar. So we first draw the Young-Baxter equation, and then we're going to fix external edges. There we go. So this time, incoming from left to right is thick, dotted, thick. And so also on the left-hand side, on the right-hand side, thick, dotted, thick. And then outgoing is thick, dotted, thick. Dotted, thick. And then you can compute that the right-hand side is B, C prime, A double prime. And then finally, A, C prime, C double prime, plus C, B prime, B double prime, which we draw the Young-Baxter equation. So this is obtained by taking incoming thick, thick, dotted, and outgoing thick, thick, dotted. Here as well, thick, thick, dotted, thick, thick, dotted. And on the right-hand side, we only have a single monomial C, A prime, A double prime. Okay, so here are our 3 non-trivial equations. And now, we did a little bit of work. We get the following. So now, we can kind of solve them, eliminate things in terms of others, and so on. So solving gives 3 equations. So the first thing that we can derive by combining them suitably is we get the condition that delta tilde, our function of ABC, should be equal to our function delta tilde of A prime, B prime, C prime. In other words, we get the same condition that we found before, that these ratios of A, B, C and A prime, B prime, C prime should be equal. I recall that this is, let me get this one, A squared plus B squared minus C squared over 2AB. And they should be equal. We get this by solving the Young-Baxter equation for all our stuff, but now we did not use the coordinate beta ansatz at all. So, drawing pictures and using algebra, we recovered one of our results from the coordinate beta ansatz without using any coordinate beta ansatz. The Young-Baxter equation actually knows about this. So this is what you get by eliminating the primed stuff in there. Moreover, what we find is that this should also be equal to the delta tilde of A double prime, B double prime, C double prime. In other words, our auxiliary R matrix is actually an R matrix in the same family of R matrices that we were already considering. It has the same value of delta. So what this means is that we can actually use the same parameterization for its entries. So we have A of U double prime is some rho double prime sinh U double prime plus eta, etc. So eta is the same because the delta should be the same. The rho double prime, of course, is just an overall normalization. You can just, everything is homogeneous in, there's only one non-primes, one primes, one double prime thing, so we cannot fix the normalization. So whatever. This is very nice. Third condition is that we find that this U double prime is actually equal to U minus U prime. So this is called the difference property. So this carries information about this complex surface, if you wish, or the complex curve on which the spectral parameters live. This is the result of the uniformization. So we have a genus zero surface, and we can uniformize our functions, and we get this difference property. But you can just get it from solving these equations. So this is also an extremely important result. These two, actually, let me write down the conclusions. The result here is that our R00 prime of U, U prime is in fact just the same as another R matrix. Actually, let me omit the subscripts here, they're not important. So we have our auxiliary R matrix with two arguments, U and U prime, and it is just equal to, well, okay, maybe some rho double prime divided by rho, and then R matrix of U minus U prime. So our auxiliary R matrix is really just one, equal with all the others. So this is extremely nice. What we see is we can actually solve this Young-Baxter equation, and we really get one of these auxiliary R matrices given our family of 6 vertex models and 2 of its special cases, 6 delta, but parameters U and U prime. Now we need to check the invertibility. So you can just compute the determinant of R of U, and you see that I guess there's an R rho to the 4th, which is irrelevant, and then we get sinh of U plus eta to the 3rd, sinh of U minus eta. So we see that it is invertible, it's okay, precisely when, if and only if, our U double prime is equal to U minus U prime. It should not be equal to plus or minus eta. And then our sinh is 2 pi I periodic. So it should also not be equal to this up to some 2 pi I k, where k is some integer. And this is certainly almost everywhere the case. There's just some discrete set of points in our complex plane that I drew somewhere where the R matrix, the auxiliary R matrix, is not invertible, and everywhere else it's invertible. So our claim here applies, and we now are guaranteed commuting transfer matrices without using coordinate beta ansatz. So we get commuting transfer matrices without coordinate beta ansatz.
Can you have other solutions for R00 prime if you don't assume the ice rule and the zero field?
I do not know if you can get more complicated solutions that would do the same job for us, but I don't think you would want to either. I mean, the simplest solution is the best, I would say. But what you can, of course, try is relax the zero field assumption on our original R matrices, so that we have A plus, A minus, B plus, B minus, and so on, and then we have an A plus prime, A minus prime, and so on. And you can try to solve for an R matrix which does not obey the zero, which also has pluses and minuses. And there, I mean, that would definitely be reasonable. I actually am not 100% sure whether that works or not. Certainly for some of it works, but maybe not in full generality. Let me give you another example, which I wanted to just write down as the very last part.
This has to be a solution just by rotating the picture. The Yang-Baxter equation is if there is
right.
the triangle, and then you rotate the triangle, you invert u and minus u, and then
that's right. So the Yang-Baxter equation is so certainly I think it is pictorially it's very natural to ask for the R matrix, the auxiliary R matrix, to be actually an R matrix, because it looks like it should be, and so this happens.
And you can even find the argument, the u minus u prime, because when you turn the triangle, there's one u which gets a minus sign. Is it possible to see it like
right,
that?
so things like this can work, but it's not completely easy to do this rigorously. I mean, it requires some extra technology. But let me give one other example. Maybe our beautiful. Now let's keep the train argument and remove this little remark. Okay, so the first remark, our claim used the entire parameterization of ABC as functions of U, but no other information of the 6-vertex model. Nothing that we used in this proof here has anything to do with the 6-vertex model. Only in the last part that I just removed, we actually used a little bit of data of the 6-vertex model. So this, comma, but no other properties. Of the 6-vertex model. So it's actually much more general, this story with the train argument. I hope it's clear why it's called the train argument. It looks a bit like we have a train on the cylinder. So another example, and I'll just outline in a few words what happens, is the following. It's the 8-vertex model. So remember, I could add these 2 extra vertices. Let me draw them here. Dotted incoming and turning into thick. And this is equal in our zero field assumption to thick coming in and dotted going out. And we call this D. So we have a 4 different vertex weights and 2 extra vertices. So we have the 8-vertex model. So here, let's solve. So now solving the Yang-Baxter equation, what you find is that the following ratios should be fixed. So we have fixed values of delta tilde, and we'll use the same symbol, but now of a, b, c, and d. And it is a squared plus b squared minus c squared minus d squared divided by twice times ab plus cd. So see, if d is 0, then we recover our old delta tilde. So it's just a little extension of our delta tilde. And there's a second ratio which should be fixed, which is called gamma tilde of a, b, c, d. And it simply is ab minus cd divided by ab plus cd. So here we see that if d is 0, then gamma tilde is 1. So this is automatically true for the 6-vertex model. But for the 8-vertex model, we have 4 different vertex weights, a, b, c, and d. We have 2 conditions, that the function delta tilde and the function gamma tilde should be constant, so we remove 2 degrees of freedom. Again, our Young-Baxter equation is homogeneous in any of these 3 different types of R matrices. So there's also an overall rescaling, which we don't care about. So we get one parameter again. So there's a parameterization. So now the next statement is there exists again entire parameterization of the ratio A, B, C, D by some spectral parameter U. This is kind of an aside which you need to do at this point. And then the Young-Baxter equation, moreover, gives the difference property again. And we find difference property that U double prime is U minus U prime, just like before. In this case, the entire parameterization uses elliptic functions, so the model is harder. But all of this works. So what it means is that we can use our claim, and it guarantees that the corresponding 8-vertex transform matrices commute with each other. Then you can repeat the computation, which I now deleted graphically. And what you will see is that the 8-vertex transfer matrix at 0 again, if we use our parameterization so that 0 is the special point, let me say more generally U star. So again, there exists a special point U star at which the R matrix becomes just a permutation. And at this point, the transfer matrix still becomes the inverse permutation operator. And then, moreover, I'm going to try to write it here. If we take the logarithmic derivative at U star of the transfer matrix of the 8-vertex model, what you get is the Hamiltonian of the x, y, z spin chain. So in the first lecture, I talked mostly about the xxz spin chain, and then briefly about the xyz spin chain. And except for this free fermion point delta 0, it is much more complicated. And beta ansatz doesn't work because it doesn't preserve the number of downspins, so we cannot fix to one of these Magnon sectors, and we could not use the coordinate beta ansatz. Then in the next lecture, we talked about the 6-vertex model. We saw that there was an 8-vertex model, but here the paths, the number of sick paths, were not conserved. And of course, you can still use all this graphical stuff. It works. So the partition function is still the trace of some power of the transfer matrix, and the transfer matrix can be cut up into local R matrices. And moreover, everything is in the right position for this claim to work. So we still know that we have a family of commuting transfer matrices, and they contain, amongst others, this XYZ spin chain. So this is very nice. So both the 6-vertex model /XXZ and 8-vertex model /XYZ fit in this picture, which was, well, I wrote up there that we have this macroscopic integrability with lots of commuting operators, and this is guaranteed by a microscopic picture of the Young-Baxter equation. And so far, we have not used any beta ansatz. Next time, I want to discuss how the beta ansatz can be redone in this Maybe a very last thing that I should remark is we have found our xxz and xyz, but from the spin chain point of view, there was this special point, the xxx spin chain. Let me this very last little bit for completeness. So how do we get to xxx? Well, we're supposed to send delta to 1, and delta is equal to cosh eta. So this should go to 1. So it means that our eta should go to 0. But from our parameterization, let me recall it, A of u is rho sinh u plus eta, B of u is rho sinh u, and C of u was independent of u, rho sinh eta. So of course, if we just send eta to 0, then we get that A becomes equal to B and C is 0. So that's not so good. So what we should do instead is we should consider A of eta times u. Then I can send eta to 0, but I get 0, so that's still not good. So let's divide this by eta. And then I can send my eta to 0, and I will get u plus 1. Likewise, b of eta u divided by eta will become u. And finally, c of eta times u, which didn't matter, divided by eta, will just become u. And actually, there's an overall scaling that I didn't remove. Sorry, c becomes just 1, so just rho. In other words, what we get, this is called the R matrix of u now is rho times u plus 1, u 1 1 u plus 1, which can be written as rho times u times the identity plus the permutation. So to wrap everything up, here we see we have an R matrix. Its entries are polynomials, but depending on normalization, so certainly rational functions of the spectral parameter. Here, for the 6-vertex model, they were trigonometric functions of the spectral parameter, and in the 8-vertex model, they're elliptic functions of the spectral parameter. So we have this sort of hierarchy where we have, from the spin chain point of view, xxx, xxz, xyz. From the vertex point, this is called the rational 6-vertex model. It's not very special. It's just this is the 6-vertex model, and this is the 8-vertex model, and the parameterization involves rational, trigonometric, and elliptic functions. So we sometimes say that the R matrix is rational, trigonometric, elliptic. So this is the spin chain. This is the vertex model. And these type of trichotomies occur quite often. So if you like supersymmetric gauge theories, then this is supposed to correspond to maybe n equals 2 in 4 dimensions, n equals 2 in 3 dimensions compactified on a circle, so you have some sort of one extra thing, and then here you go even further. This is also related to the 6-dimensional 2,0 theory. Maybe that's the better way of saying it. So it's somehow a 4D, 5D, 6D picture. And you know, if you, well, Adele knows this, but he likes geometric representation theory, then this is related to homology and cohomology, this is related to K-theory, and this is related to elliptic cohomology. And this is really close relations via work of, for instance, Krasov, Shatashvili, and so on. So now we sort of understand this from the Young-Baxter equation point of view by solving it. But that's what I, sorry for going a bit over time, but I think this is a nice point to stop. Are there any questions?
Yeah, so is there a condition on the R matrix so that there exists an R00 prime? Can I see, if you give me an R matrix, can I check some algebraic thing? Because I have 64 equations for 16 unknowns, right? So there should be very strong constraints.
Yes, right. So the system's highly.
Can I see? Is there a thing you can compute that tells you this is non-zero? There is no solution.
No. So basically, up to before today, we were talking about exact solvability, right? So I give you a model, and somehow Bethe was very clever, and then Lieb and Sutherland, and they found an exact solution to this model. They found an exact characterization of the spectrum, and with more work, you can compute other things from it. You get enough to get free energies and so on. So now we're going kind of, and then we were saying, oh, it's, the results point to hidden symmetries, and they point to underlying hidden structure, but the exact solution is just, somebody finds it, and then it's great. Now, integrability gives an underlying kind of algebraic origin of all these nice properties, and it really constructs for you basically everything that we found before, including or together with commuting Hamiltonians. But you need to have an R matrix which obeys the Young-Baxter equation to start with, right? In the end, what we really need is just a single R matrix that obeys the Young-Baxter equation. I called it auxiliary temporarily, but now we see that they're all the same. And this is a kind of an art. So finding an R matrix for your problem, this is very hard. As far as I know, what you can try to do, if you have a transfer matrix, so what we were doing here is, we said that this R matrix is unknown and these two are given. So you can try to do it, and in some cases this works. So Jimbo was able to do this actually for many examples, also for higher rank and so on. So he knew what the vertex model should be. He knew, and then he could kind of find this auxiliary R matrix. So it can be done, but I think in general, I don't think there's a clear a priori condition that tells you whether or not this can work. So this is really the initial data of a Young-Baxter integrable model is an R matrix obeying Young-Baxter.
Let's say you have a model, then you compute the R matrix using, and you still don't know if it's integral, so you don't know if there will be a solution. But...
No, you don't. I don't think there's a. No, I mean you would try the R matrix itself, but it's not going to always be so easy.
Since the first day, I don't remember which model, but you said, oh, this model is not integrable and this one is. So
right.
When you say it is not, it means that you know by some other argument that it.
Right, so this is right. So if you are given a model, how do you know whether or not it's integrable? So some people are proposing that you can compute numerically its eigenvalues, and then you can look at whether this obeys. So integrable models are supposed to have different type of statistics of eigenvalue spacings than non-integrable models. But I think people do not really agree whether or not this is really a clear-cut way to see whether this is happening. Another thing that you could do is if you have a model which has a parameter, like our XXZ spin chain where we have delta, you can numerically diagonalize it for various values of deltas. You can plot your energies as a function of delta, and then you will see that these energies are starting to move a bit. And sometimes these energy levels, well, if they cross, then this is a hallmark of integrability, whereas if they kind of repel, then, so if they don't quite touch, then this is what normally happens, and you get some sort of hybridization, you get linear combinations which are energetically more or less favorable, and those are the real eigenstates. But in the case of integrable models, there are a lot of conserved charges, so you cannot just change your eigenvectors by some linear combination because they diagonalize many more operators at the same time. And so you expect these energy levels to cross. Again, in practice, this is very hard because you need extremely fine data. I mean, how do you know that they kind of almost touch or really intersect? It's very, very hard to see. So I think there's not a clear-cut kind of diagnostic which would say this model will be integrable or not. So of course, if you find like factorized scattering, that's a good sign. If you find a result which says that there should be, that suggests that there should be hidden symmetries, then you suspect that it should be integrable. But it's not really known. And in fact, there's a model which I like a lot. It's called the Inozemtsev spin chain. There's a very complicated version of a coordinate beta ansatz. So it's exactly solvable in that sense. There is for a long time there was a proposal for explicit higher Hamiltonians, but there's only a proof that the first two in this hierarchy commute. So, whether or not it is sort of macroscopically integrable in that sense was not settled. Recently, with my collaborator, we've worked on this, and now we have a sort of a roundabout way to construct, in principle, a lot of these commuting operators. But the underlying R matrix for which it fits in this kind of scheme is not really known. So it is not. So people generally believe that that model is quantum integrable, but it is not. It's clear that it's not going to come from a transfer matrix. So I believe that there should be an R matrix underlying it, but everything works a bit differently, and this is not fully understood. And certainly, there's not yet the stuff that I will talk about next week is completely unknown. So this is really, and that's after 30 years of work on that model. So there's a lot of, this is a very hard question.